To this week's optimization for machine learning course. Sorry for the delay in this video, had a bit of a problem with the recording. Here it is. So today we're gonna do look at the practical aspects. So to see if what we learned in the previous weeks can also be interpreted in practical context and what it's actually useful for, and discuss a bit some aspects of deep learning as well. Okay. So optimization, I will try to convince you, is quite a useful tool in the middle of several aspects, like the machine learning models on the left. Then of course also the systems where it's actually run on, so hardware or software. So this is quite interesting to aim to design the training algorithms such that they actually benefit from the underlying systems. And then there's also a lot of intersections with the actual applications you want to target. So in practice, we are mostly relying on stochastic gradient descent algorithms in deep learning applications. That's clear. So what you have here is a toy example to illustrate a bit what can be the difference between like standard SGD, which you have in red. So I'm going to look a bit. If you start from this point, the black point is your initial point. You would like to get to the minimizer of this landscape here. The minimizer is actually here. This is like the lowest point on that landscape. And we can see what the different algorithms do, SGD in red. We also have AutoGrad in blue, which we discussed last week. Ada delta is basically almost the same as Adam, which we also discussed, and same for RMS prop, basically. So let's see what happens here. If you start all these algorithms, then you can see that SGD will here be the slowest algorithm. The others are doing a bit better. So for example, there's SGD with momentum, which is this acceleration addition you do to the algorithm, which we also discussed in lecture 6. I think that is the green curve here. It's doing much better than the red curve. And then we have the even more adaptive methods like AutoGrad and Adam style algorithms, which are the blue, the yellow, and the black line, which here end up fastest. So this is just an illustration. This is not how it's in real neural networks, but it is often the relative ranking of algorithms is often quite similar in real deep learning training cases. And you can also see in this toy example here already that it's actually quite tricky, right? You can get stuck into like valleys, because it's a non-convex situation. You could be slowed down in flat regions, which is basically what happens a bit for SGD here. Or if you have too much or too little momentum. So SGD here has too little momentum. Green has a bit too much momentum at the beginning and then too little at the end. So there's a lot of interesting observations you can do. If you look on the left, basically same thing, a slightly different landscape. And again, you can see that if you try here, we're trying to escape from a kind of a flat region. So here in the middle, it's quite flat. So this is a saddle point, trying to find a descent direction to escape this flat region. And you can see all methods find that, but some are managing to do that faster and some are slower. So this matters because the time you take to reach a reasonable accuracy is directly governed by this. So if you can train 10 times faster, this is giving you a saving of 10 times also in time, but also in money, because this is very compute intensive, which is also something we're going to discuss a bit more today. Okay, so some general trends in the machine learning, deep learning context. I mentioned this already, that there's quite big developments happening in industry to develop new hardware, so to better customize existing hardware for training of deep learning. For example, GPUs have evolved quite a bit, becoming more suitable for deep learning, and also other completely novel chips trying to be specifically efficient for deep learning training, where you use backpropagation to get your gradient and then use SGD on top of that. And then of course we have to discuss how several of these pieces of hardware can work together. This brings us a bit to distributed training, and a particularly interesting case of that is the case of federated learning and decentralized learning, which I'm also going to briefly touch upon today or the next week. Where here's the goal that if you have your dataset is split into many separate devices from individual people, for example, it's a bit risky to take all the data and bring it into one place and then train the machine learning model there. So instead, it would be great if the data could stay on the user's device, and these devices or phones, for example, together could already train the same machine learning model, like run SGD in a collaborative fashion, and that's what we're going to look at a bit. This brings us also to privacy. The data can be very privacy concerning. So can we still have this training if we want to respect this? Interpretability is an important topic. Not easy, as the models on deep learning side become more and more complex and more deep. For example, more parameters. And finally, one aspect I want to touch on is how to make these systems robust. So we will briefly discuss adversarial example, which is a way to break a machine learning system which is already trained. And then we also discuss briefly robust training, which is asking, so if you have many participants training together, but a few of them are malicious, can you actually tolerate that? Can you have fault tolerance built into your training scheme? All right, and the upshot on this side is just that all of these aspects are very relevant to optimization. So optimization is a tool which can help quite a few, or if not all of these aspects. Okay, let's become a little bit more concrete again. So this is the algorithm we have been talking about almost the majority of the whole course so far. The problem we're solving is a finite sum problem over the data points. So we have a data set, and every element has its own loss function, and then we would just want to minimize the finite sum of these. So we just have a sum structured objective, basically. It doesn't matter if this is data or not, but in the machine learning context, the sum comes from the data. Every data point has its own loss. You want to minimize the average loss. This is your training objective. If you look on the device, so here we illustrate the data points are maybe these vertical bars, and then you have some compute capacity, which allows you to, for example, compute the gradient of one of these partial functions. This is exactly what SGD does, so this is a recap. Hope it's not boring. You know this already. You just pick one data point at random, do the gradient of that only one function, fi, and then you have a step size in front of that gradient. So the point is that this is n times more efficient than if I have to compute the full gradient of the entire sum. So that would be a full epoch, as we call it in deep learning. There would be computing the gradient of all the points, the whole sum. That's very expensive. They can take like hours or so, for example, to get all the gradients. Whereas getting just one gradient is n times faster. So if you have 1 million data points, they can be much faster to get the gradient only of one of the points. So this is the fundamental building block for everything, as we already discussed, and today we're going to look a bit at the practical aspects. So what we see, how things evolve over the years, is that there is much more compute being spent on this algorithm. So the algorithm basically stays the same, but compute is growing, and also the people's appetite to actually spend a lot of compute and spend a lot of money to run SGD on large training data sets and also large models is increasing rapidly, has been increasing like with Moore's law over many years. So how many flops do you spend? That's on the vertical axis for your training, whereas here we have this evolution over time. And what we see is that in recent 5 years or so, this has even accelerated even more, that people spend increasing amounts of compute. So this is petaflops. times days, so which is basically just flops overall. So this, you can see that there is humongous amounts of compute being spent to train one machine learning model here. For the image-based models, this is the image classification, which was very popular a few years ago. What's nowadays extremely active and compute intensive is natural language processing. So here's one example, and then we also have reinforcement learning, which are these two examples here, where a lot of compute has to be spent because you often don't have very informative gradients there, so you need to spend even more compute to find good directions for your optimization. And so we see that the compute is increasing like very intensely. Also the size of the models is increasing. Here on this slide we look at the number of parameters in a model. We had standard image models are typically a bit smaller than this, but here we have NLP models, so for text. What these models basically do is to predict the next word. So you have an existing text, and this model is able to continue your text, predicting what's the next word and the next word, so you can generate text. That's what basically all these modern NLP models are trained on. The interesting thing is that this can be done unsupervised. You just train the model to predict existing text, to always find the continuation of every text in the world. At every word it is trained to predict the next word. It's like a multi-class classifier. So the good thing is, because you don't need labeled data on this, you can train it on very large amounts of unlabeled data. And because you have so much data, you can then also train this on quite large models. By the way, this type of training is called unsupervised training or self-supervised training, which is even a better name, or contrastive training, that you're trying to predict if the next word is the actual real one or it's a fake one. For example, a random one, which is not the correct one. So this kind of self-supervised or contrastive training is used to train basically all currently state-of-the-art natural language processing models, including also BERT. But the point here is not to understand these models, which are based on self-attention, by the way. That's why they call transformers. That's not the point of this slide. The point here is to just say that the number of parameters of these models has increased quite a bit. So this model by OpenAI, like 100 million parameters, and BERT has 300 million parameters, which you're training, which is quite a lot already. And then so more recent models here can grow to much larger amounts of parameters, up to like 8 billion here. Or here's the same thing, including one more model, which goes up to like 17 billion parameters in one model. So this is a big model, but this is also quite successful. To some a bit surprisingly, because these models work really well even if they have more parameters than you have training examples. I mean, here we do have humongous amounts of training examples as well, but even if you would use less training examples, even then SGD on training such large models with many parameters works surprisingly well. So that means we better make sure we also have efficient optimization algorithms to train these things. Okay, if you look at the systems to do this, this we already mentioned, we have like many data points on one machine depending on its memory capacity, and we have some compute. And we might also have several of these compute devices. It can be computers or clusters or mobile phones. And then these devices increasingly also have some accelerator chips in addition to the standard capacity, for example a graphic card or a customized chip, for example. What we have to do now is we have to figure out, if we run SGD on such a system, how do these devices talk to each other, on different levels, how to really make this efficient. And that's what I want to talk a bit about in the next 10 minutes or so. The big question here is the following. It's just, so we saw it, right? We need so much compute to train modern deep learning models. So it's a very natural question, is just how much can you parallelize it? So let's say, okay, we agree we need this much compute, but can I train it 100 times faster if I have 100 times more machines? That is the question. And it's quite a difficult question because it's not so clear what is the fundamental limit. So if you have a billion weights in your neural network, how many computers can you add such a training still gets a speed up when you add more computers? So it seems hard to push this very far, right? It seems hard to ask. I probably cannot have as many compute units as I have weights in my network. That would be far too much. I mean, then basically every weight will only have a small number of floating point operations it contributes to. So at some point there will be an interesting slowdown happening. And it's not clear what algorithm is best to actually harvest the maximum amount of parallelizability. Maybe there are several things you can do to squeeze out as much parallelizability as you can. So let's see what's the easiest way to parallelize SGD for training. Okay, so let's formalize this a bit more. If you just want to parallelize over these 5 machines, so we call this distributed training as well. In this case, we will just have our data is now split into 5 machines. I mean, sometimes you can give all the data to every machine, but the more realistic setting is that the entire data is partitioned into 5. So first machine has the first part, second machine has a different small part of the data, and everyone has their own part. And now we want to run stochastic gradient descent. Well, that stochastic gradient descent will actually work, but is there actually a simpler algorithm? Could we just naively parallelize it? Could we just let every machine train their own model and then average the results, and then we'd be done? And the answer is unfortunately no. It's not so easy. So you can't just have every machine train their own deep net on the local data and then average the resulting models. That's called one-shot averaging. And why this doesn't work, here's a very simple example. When every machine just has 2 data points and we are trying to find a linear classifier to separate these data points. So my first machine is here. It's very easy, right? I have these 2 data points on my machine. I'm trying to find a linear classifier. Here's my best solution. Okay, so if you don't like this linear classifier stuff, this geometric interpretation, just think that this is I have my f1 loss function of my parameters w or x. So if I have this good parameter here, then I have that my loss function of my first machine is 0. So I found a classifier. This is one parameter model, W0, W1, where is this classifier? So I have 0 loss because every point is on the correct side. If you remember this from standard machine learning course, on the linear classifier, if you have, for example, hinge loss or anything, if the point is on the correct side, let's assume then we have 0 loss. So here we have 0 loss, we are happy. We have minimized the first loss function, that's great. However, the other machines, they do this differently, so they have their own loss function. So machine F2 tries to find a different linear classifier such that its own 2 data points are separated. and that here is completely different, right? So you just do this on every machine. Every machine finds a weight vector, which is just one weight in this case, such that its own data has zero loss or minimum loss. So good, we got this. So we got these 5 classifiers, and now we average the W's of each of these 5 machines. The resulting average is this one. Sorry. The resulting average will be roughly will look like something like this. So if you average these guys, the set of the W parameters. So you can see this is not a good classifier. It's not the correct classifier which separates all the 10 points. It separates most of the points fine, but this one is completely wrong. So average is wrong. What you would want to have is you would want to have this classifier. So this one would be the correct one. And what I'm saying here is that just every one of these 5 machines minimizing their individual loss function and then averaging the resulting W's, that is not correct. The average of the minimizers of 5 different loss functions is not the minimizer of the average loss function. That's what's happening here. So maybe I can try to write this. So the point here is that the minimizer of the average, that's what we want, right? We want to minimize the average loss over all data. Is not and I actually should write argmin. So average argmin of these FIs is not the same as the true thing we want, which is the minimum of the average. So, and sorry, I don't have an eraser here. The W which minimizes the average, that's what we want. That is not the same as the average of the minimizers, of course. So that's a problem. Therefore we need to be careful. Therefore, training machine learning models is not naively parallelizable. That's the summary. So even for this simple case of linear classifier, even there, finding the solution of the whole data set, which is all the 5 machines together, is not the same as finding the solution of the global problem, right? Is not the same as when you just average the solutions of the 5 machines. Therefore, we need to be more careful. We need to have some non-trivial parallelization where we communicate between the machines more than once, right? Not just at the end after everyone has done their own job. So let's see how that goes, and it's actually not so hard. You can have algorithms which converge here, which are based on gradient descent, of course. So what we just discussed previously was this thing on the bottom. That's just what does not work. Basically, to never communicate except at the end, to average the resulting models. That does not work. What does work is just to run SGD together. This we kind of know because we know that SGD converges at least on convex functions. We even know that it does converge to a flat point on non-convex function, a point where a gradient becomes 0. So if we can have SGD happening here, meaning that we have a mini batch where all machines contribute a bit to that mini batch. For example, here we have a mini batch of 5, of size 5 data points, every machine has contributed one data point to that mini batch. Therefore, we get the average of these 5 gradients. We send that average after every computation of the gradient. We send it to a server and we add the gradients, these 5 points together. We add it to our old model, and then we send back the result to everybody. So everybody will always have the same model W in this scheme. And then we have to repeat this many, many times. So for every SGD step, we have a communication round. So as many data points we read or compute the gradients for, we also have that many communications. So it has a lot of communication, but it does actually work as opposed to one-shot averaging, which fails. Okay, so we need to look more into this, and that's also the algorithm which is actually used in deep learning. It's the most common way to parallelize deep learning training. One aspect we should not forget is communication cost. So now we computed these gradients, but now we have to send them to a server, or we have to send them to everybody else, to another machine. Here is some realistic example. If you have 100 parameters, 100 floating point numbers, so let's say your gradient has this size, which means your model has this size. So reading this from RAM is fine, very fast. Takes about 1 nanosecond per parameter, something like this. However, if you would do this over Ethernet, so then sending the same 100 numbers, that would be a lot slower, for example, maybe 1,000 times, 5,000 times slower. And even more so if you have like MapReduce, which is one particular kind of communication scheme to have a reduce operation, meaning every one is able to sum up or average their vector. That's what we need here, but this is very slow if you do this with traditional MapReduce systems such as Spark, for example, which you can see here, because they have too much overhead. If you want to do this communication 1,000,000 times, it's much too slow. If you just want to do it once, then this overhead is completely fine. So what you have here is time on the logarithmic scale of training a linear large classifier on a large set of data, and on the left we have the suboptimality, so the function value which you try to bring down. And then you can see if you have this good old C++ communication scheme, which is called NPI, that has very little communication overhead because it's a low level close to hardware, whereas other schemes would have a bit slower convergence here because their communication cost will be higher because there's more overhead. Okay, communication, we get back to that in a second, but now let's think again about how to most easily get parallelization. So one thing is, so if I just add more machines, can I get faster training? So, and that's exactly what we have on this plot here. So the easiest way to just get parallelization is just to just make your batch larger. And that is exactly what we have actually seen before. We just have seen on when we discussed SGD here, we've seen that, okay, you have now 5 machines, sorry, here. So if I just have one machine working alone, I would have a batch size of 1, but now I have a batch size of 5 because I have 5 machines. So in every time step, I will compute 5 times as many gradients compared to just having one machine. So the question is, am I actually 5 times faster? So that would be nice because I spend 5 times more compute, but I have parallelized it over 5 machines. So this is hopefully what's going to happen. And we already know this from the theory we saw on convex convergence of SGD. We saw that the batch size is directly acting the same as the number of steps. So if you have a higher batch size, you get a faster conversion. So your convergence is like batch size times t, 1 over these two guys. So if you have a 5 times larger batch, you actually converge 5 times faster, basically, up to some limit. that's a quick, slightly simplified picture. But now you can ask, so is this true even if you have increased the batch size even more? So what you have here is a double logarithmic plot of the batch size I use compared to the number of steps I need to reach my target accuracy. This is just validation accuracy. I want to reach whatever, 99% accuracy. How many steps do I need for that? And the step here is just that every machine does one batch, does their local batch, which is, for example, one data point. But then I have this many global data points, so this many machines globally. So if the point here is if I double the number of machines, which means I double the batch size in total, then hopefully my cost is gonna divide by 2. The number of steps is gonna be halved if I double the number of machines. That's what perfect parallelization would be. Perfect scaling would mean that you are exactly staying on this 45-degree line, diagonal line, that having 100 times more machines means I need 100 times less steps. That would be the perfect world. But this is a very interesting thing, which was kind of studied only like 2 years ago, that it's actually not the case. The world is not as ideal. So in deep learning, you can increase your batch size quite a bit. At the beginning, you do have this nice scaling, but once the batch size gets larger, then you have a slowdown here. So you don't get this perfect scaling anymore. But you keep adding more machines, but that you don't get a speed up anymore. You don't need fewer steps, even if you add many more machines. So here it becomes completely useless to add 10 times more machine, because it does not make you converge fewer steps. So you do not get any improvement in your speed. So why would you add more machines if you can get the same accuracy with even fewer machines in the same number of steps? So the batch size here in the very extreme case goes up to 100% of n, where n is the number of data points. So that means I have one epoch. So then what you have here is that you actually have GD instead of here you have SGD in the standard form, which is one point in your batch. If you have the smallest batch size, and if you have the largest batch size, then you have full gradient descent, which is fully deterministic. So there's no randomness anymore. And that's actually also very related to why it fails. So this is still not completely explained in theory, but what people think is that it's exactly because of the randomness. Because the reason why SGD works so well in terms of test accuracy, well, there are many reasons, not all of them are known, but one contributing factor to the success of SGD on training these non-convex deep landscapes is the fact that SGD has a lot of randomness, which makes it run better and have a better test accuracy and be less confused by local small irregularities of the full objective functions. So having this noise allows SGD to actually simplify the landscape a bit and make more substantial, more meaningful progress, especially in terms of the test accuracy. When your batch becomes very large, then this randomness or noise goes away. So then you don't have randomness anymore, then the resulting gradient is completely determined, and then you do not have this simplification through the noise anymore. Your variance disappears, and then you do not get a speed up anymore, which is one type of explanation, but this is still an active kind of research area. So what to get from this is, well, rule of thumb is as soon as your batch size reaches like maybe 10% or 50% of the full data set, which is n, then you should need to be worried about this. So if you have a small data set with like 1,000 points, and then you can maybe not benefit from 100 machines, well, that's very hard anyway, because you will be hurt by communication cost. But only if you have a like very, very large data set, you can also benefit easily from SGD with larger overall batch sizes. And so the other reason we want large batch size is actually, well, there are two reasons. One of which we have seen here is just to get speed up. And the other reason we want large batch size is also that we want to avoid communication. And that is illustrated a bit here. So if you look at the right, we have mini batch SGD on 2 devices. And we have, here we have that after every, in every step, the machine has a mini batch of 2 locally. And so I pick not one data point on my own machine, but 2 of them. And then I send the average of this mini batch to the server, and the other machine does the same. What's the point here? The point is that because I have 2 data points at a time, so the communication, compute or communication is like 2. So I can compute 2 gradients, and I only need to communicate 1. So I only need to communicate 1 vector. So that's why having a local mini batch is a very good idea, because then if you have a local mini batch size of 10, then you can have 10 gradient computations. You can keep your machine busy while you need to wait for communication. So it's a very good idea if communication is much slower than computing 1 gradient, which is typically the case, even for deep nets. So this is why mini batch on 1 machine is a good idea. However, you could say, okay, maybe that's still not enough. At some point, your device can just not, due to capacity, cannot have more mini batches, because in deep learning, that's what GPUs do, right? GPUs allow you to compute the gradients of several data points at the same parameter vector W at the same time, right? So same W prime, few different data points, like 100 data points in my mini batch. The GPU gives me the gradients of all of these 100 using backpropagation. Well, what's the limit here? So why can't we just have as many points as we want? The problem is backpropagation needs memory. So if you do this propagation forward from the input of your neural network to the output, you need to remember all this activation, so that when the backward pass of backpropagation happens, you still have this activation, so that you can multiply them with the gradients to actually get, with the chain rule, to get the correct gradient. So, and this is different for every data point. So for every data point you need to store a full set of activations, which is as big as the model, roughly, in backpropagation. So that's why backpropagation needs a lot of memory, especially if you make the batch size larger. Then you need as much memory as you have elements in your batch. So you need to store this many models. And we saw that 1 model can be quite big already. It's 300 million parameters for 1 model in BERT. That's why, and now you just multiply that with your batch size. If you have, that's why actually for training BERT, people cannot use typical batch sizes of like 100 or so, which we are used to from images. But for BERT, you can only store like I think around 10 or so models on a GPU with maybe 30 gigs of RAM. So you can only have a relatively smaller batch size of 10, and then your memory is full. So I cannot increase my batch size further, so that's what I do. Now the question is that enough? Is my batch size of 10 enough to balance compute and the time to communicate? And maybe it's not. So maybe here I will still be waiting for communication. For example, in BERT training, I will wait until this big model arrives from my collaborator machine. I don't want to wait for that, so is there anything I can do? What you can do is local SGD. So it's also called local update SGD, which is just here, okay, I'm doing the same thing, I have my local batch, but I don't have time to wait for the other machine to get their contribution. So what I do is I just continue on my own data. I will just continue locally. I will pretend the other machine is not there. I will just do stochastic gradient descent on my data. I will do 3 steps here of stochastic gradient descent only on my data. That's a bit wrong because we don't want stochastic gradient descent on that data alone. We want stochastic gradient descent on the joint data of both machines. That's what's happening on the right. Here we have a bit of a mix. We have 3 stochastic gradient descent steps only on the local data, so we kind of specialize a bit too much for our local data. We overfit a little bit to our local data, but after we've done these 3 steps, then we average with the other machine. So then we average the resulting models we have, which is what we did in the mini batch case as well. And the point here is that now I have a communication versus compute ratio, which is a bit different. So now communication happens once and compute happened 6 times. So this is a much better ratio if your communication is slow, which is typically the case. So here I have 3 times less communication than I had in the mini batch case on the right. So that's one a good approach. Once you have reached the problems of large batches, either because your GPU is full or because what you have seen previously, that your batch is too large already mathematically, you don't get speed up anymore, then this idea here is a very good way to get additional parallelization while having the compute being slow. And this is actually also the most popular algorithm in federated learning, which is, for example, used on your mobile phone, on your Android keyboard, because people want to train the keyboard to have the next word prediction, because that's what you use in writing every time you write anything. But what you write is very sensitive, so it's better if this training happens, if the data for the training happens on your device. So they use exactly this algorithm, which is called federated averaging as well. We will get to that a bit, I think, next week or end of this lecture today. All right, that is parallel SGD, and talking a bit about the communication ratio. Another small aspect of it is sometimes you have stragglers. So sometimes not all machines are the same speed, so sometimes you need to wait for one slow machine happening. For example, here, machine 2 is faster than this one, so that the slower one has to wait with the averaging of everyone's gradient. Can we get rid of that? Not so easy, but sometimes we can. Sometimes we can allow an asynchronous model that machine 2 just goes on and writes all their updates to, for example, shared memory. Then you have to think about locks and thing and to avoid conflicts. But you could just do your updates, write them whenever you have them, and you also need to read the model whenever you need a new batch. And then there is convergence analysis for such variants of SGD as well. They're a little bit more challenging, and then you need to introduce some assumptions on what kind of delays do you actually have, how much can you tolerate. Maybe there is like a maximum delay you have for machines. Then it's quite easy to prove that the convergence is still okay. However, in real world, you often have very bad extreme delays, right? Some kind of long tail, or so that some machines fail very badly, especially if there are a lot of machines. And then it becomes a bit more challenging to theoretically analyze stochastic gradient descent in such a scenario. But there is this kind of small, speed up you can get by allowing this asynchronicity. There are some simpler variants which just say, okay, if a machine has too much delay, then you just ignore it, delete it. So you're just synchronous, but the ones which are too long, you just cut them and go on with what everyone else has. That's an engineering approach, I would say, to the same problem. Okay. So communication, we talked a little bit about it before. We said, can we have more compute so that the compute and the communication between the machines are better balanced? We said one way to achieve that is to just increase the mini-batch size or to have local updates before you communicate. Another way is to actually compress what you communicate. So what we did before is, we always sending models, or we sending delta of models, so the change of a model. That's what we send. So we send this big vector corresponding to the changes in all weights. This is as big as the model, right? So this is very costly. So can we send less? There are a few approaches here, for example, quantization, which means instead of sending an accurate version of my gradient or of my model, I can send a lower accuracy or lower bit resolution of these numbers. So for every floating point number in my entry of my vector I want to send is, for example, 32 bits. But now what I do is I only send like a smaller version, like 8 bits per entry, or if you want to be extreme, you can send 1 bit per entry. Then what you get is a 32x reduction in the amount of data you send. So that is in some cases possible. So the question is now, how low can you go? Is it still going to give you that much improvement in your model if you perform this SGD step, but then the resulting gradient, you have kind of crippled it by doing this drastic reduction or discretization? So that we're going to come back to that on the next slide briefly. An even more popular variant of this quantization or compression is to just not send most of the entries, but only send the very biggest entries of the vector you want to send. So, well, what you send is, for example, the gradient. What you then do is, I would only send maybe the 1% highest entries in magnitude of that gradient, and all the other ones I will just not send. So I only send this sparse vector, which has 1% non-zeros. Or if you want to get even more improvements, then you can have a rank 1 approximation of your gradient. What do you mean is the gradient now a vector or a matrix? That's a strange thing. But the layers are actually matrices, so the weight vectors in a layer, they have very naturally they appear as a matrix, so you can take that form. It's just a rewriting of or regrouping of your vector, and you can ask, okay, maybe it's a nice idea to send a rank 1 approximation of that matrix. And if you have a big layer, especially for fully connected layers, that can give a very big reduction. From originally you have n squared weights if you have n neurons input output, but now you only send n. So from n squared to n, this is a big reduction when n is the number of neurons. Here is visualizing this a little bit. So that's what I just said. So maybe you have n neurons input and n neurons output to a layer. So this is how your gradient looks like. And what we discussed on the previous slide is, okay, I can just send maybe the signs instead of these actual floating point numbers. Then what I would send over the wire would look like this. If I do the top k, so the k entries which are highest in magnitude, what I would send would look like this. And then you can also have other structures of sparsity. You could send a random bunch of entries that works quite okay, or the rank 1, which you think actually works best. Okay, what's interesting is here, if you use, this is for sine SGD, which is what we just mentioned, so that if you only send the signs of each entry of our gradients. So here is your current model, and then this vector here, maybe I should use different colors. So So this is the sine of my gradient. It doesn't matter, stochastic gradient or full gradient. So this is what would happen, right? If instead of using the actual gradient, you use its sine. So we discussed this last week actually. It's a very interesting algorithm. It's actually surprisingly working very well on deep learning, and I explained you last week a bit why we think that is, because it's very close to what Adam would do. But this one is even much simpler. But here is an example where I'm going to prove to you that it actually does not work. So it fails on very simple functions already. The function we optimize here is just like two linear functions. You want to go down here, but so we want to go somewhere here to our minimizer. So we want to walk in the true gradient direction. That's the g here. But what we actually do is we walk in this s direction here, which is the sine of the g1 vector, or gradient vector. So we stay on this diagonal here instead of going to the true direction. And then let's say our next point, this is our next w, this is w at time t plus 1, here is w at time t. So the next point we are here, and again we take the sine of the gradient, so then we actually stay always on this line. So we can never move away from this line. We always move back and forth on this line, even on this very simple toy function, but we will never get the opportunity to go to this optimal here. So the optimum is w star, because we have no way to ever move away from this line, so we are stuck on the blue line. So sine SGD fails on very simple examples, even in 2 dimensions. If you want to get more details, here is the definition of that function, if you want to play around with this in Python. So it can fail, but sometimes it still works, surprisingly. There is a very nice kind of way to solve this problem and to make it work, because it's attractive, right? It's attractive for several reasons. First of all, it avoids this kind of gradient explosion, which is attractive in deep learning. And then, more importantly here, because it's attractive, because it allows us to save 32x in communication, and so it would be quite nice if you can use it. So the way to use it correctly, make it work, probably, is to use this kind of error compensation or error feedback. And that is a very simple trick. So instead of using this sine g, that's our compressed gradient, and then g here is the true gradient. So we would like to move to the blue direction, the true gradient, but we do move in the green direction, the compressed sine gradient. So there is okay, to make this work, we just need to accumulate the errors and not forget about the error in every step. So the problem why the thing on the previous slide failed was because we always forgot about the error. We never realized that there's a very systematic error, which is this green arrow. Sorry, the 2 red arrows. In every step, I have an error which is in the same direction. So I never took account that in every step I have an error in the same direction. So I should kind of add up these errors and not forget them in every step. Why I was stuck on the blue line is because I every time forgot about the error. So to make it work, we need to remember the error. So the parameter is called w or theta. It doesn't matter. So we just do a next step. So again, we actually use the compressed gradient here. Compressed is green, and then we want to use the true gradient again. But what we do now is, before we compress, is that we actually compress not only the current gradient, but we compress the current gradient g here plus the error. So so this error stuff is important because we have it. We know what we wanted to do and what we then did not, right? So we wanted to move here, but we did not because we compressed. So if you just remember that, and then the next time we add this error, we still know, so we account for it, and we compress the gradient plus the error we have, then this is enough to actually fix the whole problem. And then you actually go here, and then you can prove that this one stays very close to a true SGD trajectory. It actually stays close to exactly this red arrow. So how you prove this is you have this kind of virtual trajectory, which would have been the true SGD, but you have moved on this different sequence. And the sequences are very close. How close are they? That's exactly the red arrow, if you want to prove this. But we don't want to prove this, we just want to get the idea. The idea is you just accumulate the error in every step. You can do this for every compressor, not only for sine, and this actually then, here is the definition of what is a good compressor, and then here's the convergence rate you get, which is basically the same convergence rate as we had for SGD, and now it's for a compressed version, so every gradient you send is compressed, so you send C of x is the compressed version. That was like the sine of this shouldn't be called x, and it's better to call it g because it's applied to the gradient. So if delta is this quality parameter, so if it's 0, it's very bad quality. If it's 1, then it's perfect quality. You have perfect accuracy. So whatever your compression operator is, all the ones I showed you have some delta. Whatever the delta is it will not slow down your convergence rate very much. It will only affect the kind of the first term. And this convergence rate here is for non-convex objectives, which is what we actually saw when we talked about the gradient norm becoming small, or even on non-convex functions. Remember, that was when we said gradient descent converges to a stationary point. The same is true for SGD if you talk about convergence at this average of your past iterates. So that we have that for SGD, but do we also have it if we compress the gradient at every step? And the answer is yes. You get roughly the same convergence rate. So we have not precisely seen the proof of this convergence rate in the course, but you have seen the one for GD, so not SGD, and you could do exactly the same there. The proofs are the same basically. Okay, one trick to get additional communication savings. So that's all for communication. So let's take a step back and let's discuss some other aspects as well. So for example, it's of course also very important that we can adapt to all the compute we have, and for example the memory we have. As we discussed at the very beginning, the size of the machine learning models is increasing a lot. So sometimes even just in terms of memory, they become too large to, for example, store on a model on a mobile phone. For example, a BERT model, is you train this on some server GPUs, it's fine, but it has 300 million parameters. So to store 300 million floats on your phone, that actually will break the, well, not the storage, but it will break the RAM of your phone, so you cannot deploy BERT directly. So you need to ask, can we make this more compact in terms of memory and also in terms of compute? So on the phone there's less compute capacity. Is there some compute we can save when we use a model, or, well, using a model, I just mean make predictions on a trained deep net, or to even train with it, that would mean, can we compute the gradients? So deploying on low resource devices like phones or just a large variety of devices, that is a challenging question, and there's some nice things that can be done here as well. And that's it's called model compression. Model compression just means I have my deep net, but the question is, can I find a smaller version of it? There's so many weights here, right? there are just too many, I cannot store all of them on memory. So is there maybe a sparse version of this deep net, which is here only the red arrows, such that if I only use the red weights, maybe I get a similar accuracy? That would be nice, right? So that here you get the input to your neural net. It goes through this, every neuron has activation, then the weights, which you have in black and in red, if for the smaller version. And then on the right you have the output of the net, of the neural net, which is, for example, your final output of classification. Okay, so if there is a sparse version of that net, which would be just the red weights, the red connections, then we would be happy. And it turns out, yes, this is often possible. The question is just, how do you find these red weights? So you have a dense trained neural net which is given, which is the black arrows, black lines. And now what the simplest thing you can do is again prune them by magnitude, which means only keep the weights of a big magnitude and the other ones you set to 0. That's one easy thing you can do, and this is also called like pruning. And turns out you can maybe 90% of your weights you can set them to 0. So then you have a model which is 10 times smaller, and you can say, okay, it's maybe slightly worse than the original model, but not much. So it's actually quite surprising that the accuracy of the pruned model is quite okay. It's this, for example, for image classification models, you lose very little, like less than 1% in accuracy you have to pay, while reducing the size of your model by 10 times, which is a nice property. If you need 10 times less storage then you can actually deploy it on your mobile phone. So this is a memory advantage. It's also a compute advantage in some sense. So because now if you use this model, you only need to use the red weights, so you have much less flops, much less multiplications and additions to compute the output given the input. So it's roughly, you could say it's maybe in a sparse case, well, it's realistic to say that it's also the compute goes down by 10 times. However, the compute now has a bit of different structure, so now it becomes actually a sparse computation, which are not as easy to parallelize. For example, on the GPU, you cannot compute the output of these red lines easily 10 times faster, because now it's not a dense matrix vector multiplication anymore, but now it's a sparse matrix which is multiplied by the vector. So yeah, computing the output of a neural network is always just matrix vector. So the vector is the input, the matrix is the layer. So we need all these matrix vector operations, and even backpropagation will be again matrix vector multiplications. So matrix vector multiplications can be fast if you have many cores, right? You can easily benefit from single instruction multiple data. You can benefit if it's a dense matrix, right? But if it's a sparse matrix like now, then it's a bit harder to get easy speed up, for example, on a GPU. But if you have a more flexible chip which supports sparse operations, then you can get even a compute speed up. And that's also an active research topic, and you can ask, okay, maybe depending on how you identify the pattern which you retain, maybe you can identify a pattern which is even much more compute beneficial. That would be nice, and that's something that people are also working on the research side. Maybe there's a bit of a different kind of patterns you can use for convolutional neural networks than the patterns you use maybe for transformer networks. But still many open questions. Okay, so we talked a lot about parallelizing by parallelizing the data. So everyone has their own data and they work together in training, and that is a very nice and well understood way to parallelize training. It's actually the really dominating way. Most of the parallelization is happening that way currently in the industry. There is a different way to parallelize training, which is a kind of orthogonal, so it can be done independently of what we discussed. And that is to parallelize by giving different parts of your model to different workers. So this is called model parallel. It's a bit more challenging, but the idea is simple. If my network is too big to fit onto one device, I just give a bunch of layers to one device and a bunch of other layers to the other device, and then when they compute the forward pass from input to output, they have to talk to each other, so it's very compute intensive, communication intensive. And then when they compute the gradients, they have to again communicate with each other. So there is quite a few algorithms at the moment trying to make this efficient. For example, you can do some pipelining. So while a few input points are running through the forward pass, once the first batch is through, you can already feed in the next batch in the back, so that every worker keeps being busy and that it doesn't have to wait 8 steps until the result of my current batch comes back. So this is an interesting area and is also used sometimes in practice, a bit more annoying to program this. Okay, that is it for today, and then next week will actually be the last week where we have lectures, and then the final week we give to you for your projects as a compensation for the holiday, which is actually today as well. But then you have to organize your own time to work on the projects, and you'll be more flexible. So I hope that the course today and also next week, the video, will help you a bit for the practical aspects to identify some interesting scenarios maybe which you can study for your project, because there the goal is really to study experimentally some aspect of these optimization algorithms, which ones actually do matter maybe for practical training. Okay, next week we'll discuss a bit more on federated learning and decentralized learning, and then we'll summarize and see you next week. Thanks.